Hello everyone, welcome to the second day of the second Astrobiology live presentation series. I hope you and your loved ones are safe and sound. Let me introduce myself. I am Özge İdil Geçimli. I'm second year Metallurgical and Materials Engineering student at Middle East Technical University. Today I will be your moderator and hosting our precious guests. In this session, Ian Crawford, who is a professor at Birkbeck University of London, will be with us with his presentation. He believes that space exploration is very important for humanity and has studies such as the lunar surface as a recorder of astrophysical processes and assessment of the survival of biomarkers in terrestrial material affecting the lunar surface. If you come up with a question while watching, please do not hesitate to ask through the chat box. Because at the end of the presentation, there will be a Q&A session, and I will deliver your questions to Mr. Crawford. Now, Professor Ian Crawford is with us with his presentation called The Astrobiological Case for Exploring the Moon. Welcome, sir. How are you?
Oh, I'm very well, thank you.
Thank you. Now the stage is yours, sir.
Okay, thank you very much. Well, good afternoon, everybody. It's a great pleasure to be here to give this talk to the Middle Eastern Technical University about astrobiology. So astrobiology has interested me for a long time, and this afternoon I'm going to try and convince you that exploring the moon is also important for astrobiology. Of course, since the moon is dead, as far as we know, and has no life of its own and has never had any life of its own, it seems a bit strange at first sight to be talking about doing astrobiology on the moon. But obviously places like Mars and Europa and other places in the solar system are more habitable places to search for life in the universe. But I just draw your attention to this beautiful photograph. This is an image of the Earth and Moon taken together. It was taken by the US Galileo spacecraft on its way to Jupiter in the 1990s, and it's looking back, and it contrasts our beautiful blue planet with its clouds and its oceans and its water and the seemingly rather dead and boring sterile surface of the moon. But then, of course, this planet of ours, the Earth, is currently the only place we know of in the whole universe on which life has evolved. And so obviously astrobiology is a science. We're trying to find out whether there are any other planets like the Earth in the universe, but we don't know. And currently the Earth is the only known inhabited planet in the whole universe. And during all of that time, the moon has been with us. For the last 4,500 million years, the moon has been orbiting the Earth, kind of keeping watch, but also keeping a record of things that have been happening in the space environment which have affected life on Earth. And this is one of the main reasons why I think the moon is important for astrobiology. So if I draw your attention first to the photograph at the bottom, this is from the Apollo missions, of course. This is a picture of Jack Schmitt, who was an Apollo 17 astronaut, walking on the surface of the moon here in December 1972. Notice the moon buggy, lunar roving vehicle, it parked over here. Anyway, I show this picture to make a point about the lunar surface. The moon has no atmosphere and it has no magnetic field, and therefore the lunar surface has been exposed to space totally unprotected from the space environment for thousands of millions of years, which means it's kind of acted as a giant museum of activities that have been going on in space. So these would include meteorite fluxes into the inner solar system, cosmic rays, solar wind, maybe other things as well, which we would like to know about because they will also have affected life on Earth. But the Earth, as a very geologically and meteorologically active planet, has destroyed most of its early history, and this history is preserved on the moon. So this is one of the main reasons why I think exploring the moon is important for understanding the history of the Earth. And the history of the Earth is important for astrobiology because the Earth is the only known planet in the universe that we actually know life has evolved upon. So I've got this rather long list of bullet points, which I'm going to sort of build my talk around, starting off with perhaps what seems at first sight quite a boring reason for wanting to explore the moon. I've written characterization of the impact cratering rate in the inner solar system. But then the rate at which meteorites have been striking the moon will be the same or very similar to the rate at which meteorites have been striking the Earth. And they, as we know, can be very important for the history of biological evolution on the Earth. And the moon contains a complete record of this impact history. We've now learned that craters at the poles of the moon, very cold craters that never see the sun, are probably harboring ice, water ice, maybe other ices, maybe organic compounds delivered to the moon by comets and asteroids from elsewhere in the solar system. So there's a record here on the moon potentially of the rate at which water, volatiles, organic compounds have been delivered to the moon, but that will be the same as the rate at which these things have been delivered to the Earth as well. So the moon may preserve a record of all of that history. Then, since we find meteorites from the moon on the Earth, about 200 or something, probably there are meteorites from the Earth on the moon. And some of these meteorites from the Earth might date from the very earliest history of the Earth, say 4,000 million years ago, and the Earth has not retained any rocks of that age. So strangely, some of the very earliest Earth rocks containing biosignatures and evidence for the early evolution of life on Earth, we might find those on the moon. Similarly, we might expect to find a record of the activity of the sun and the galaxy on the moon implanted into these lunar soils as solar wind and cosmic ray particles, which might have been important for the history of life on Earth. We might also find some really exotic things on the moon that we don't expect. So I've written here alien artifacts, question mark. So who knows? That seems a bit exotic. So, but anyway, I will say something about it later, because I think we should maybe keep an open mind to that. Since we have sent many spacecraft to the moon over the course of the space age, and many of these spacecraft will have had microorganisms living within them, it would be interesting from an astrobiology point of view to see whether any of these microorganisms have survived in the lunar environment for many decades, because this would help us understand how life, or whether life, can survive in a space environment. And this will be relevant for planetary protection, designing planetary protection protocols when we send spacecraft elsewhere in the solar system. And it may also be of interest to assess the theory of panspermia, which is the idea that life might have arisen, might travel between planets on meteorites. We may be able to put some constraints on how life can survive in space environment by seeing whether life has survived on some of our own crashed spacecraft on the moon. And then in addition to all of this, exploring the moon will help prepare us develop the tools, the technology, the protocols for exploring elsewhere in the solar system, and especially Mars. And of course, there are a huge number of astrobiology reasons for wanting to explore Mars, but that would be a different talk. So starting off with perhaps the more boring of these things on my list, the characterization of Earth's impact flux. So here the photograph shows some craters. This is this big crater Daedalus on the far side of the moon, but I just show it here to show that the moon has millions of impact craters, because the moon has no atmosphere and no way of eroding craters, so it just collects them. Which means the moon has a complete record of the rate at which meteorites have been striking the surface of the moon throughout the whole history of the solar system. But since the moon has been orbiting the Earth for all of this time, the rate of meteorite bombardment of the moon will be the same as the rate of meteorite bombardment on the Earth, more or less. So the moon has a record of the impact flux onto the early Earth through time. And this is of astrobiological interest, because if we look at the big graph, the graph shows the age of the surfaces of the moon or the Earth. These numbers are in billions of years. So the first half of the history of the solar system is shown here, from 2.5 to 4.5 billion years ago. And then there are some estimates for the impact flux relative to the present time. But notice this is a logarithmic scale. So 0 here is the present flux. 2 would be 100 times. 6 would be 1,000,000 times the current impact flux. So there's a huge range in the impact flux in the early solar system. This is called the period of heavy bombardment. But what we don't know is exactly how heavy the heavy bombardment was. So this graph shows 2 possibilities, both consistent with our current knowledge. Either a very steep decline in meteorite cratering rate, then a bit of a flat, quiet period, then a sudden peak in the bombardment history about 3.8 billion years ago, decaying back to the present. Or the impact flux might have followed a more smoother, sort of more monotonic decline. I mean, these are exponential because it's a logarithmic graph, but a smoother decline through time. And we don't currently know, because none of the Apollo missions sampled rocks or lunar surfaces older than about 3.8 thousand million years old. So if we want to know what the impact flux on the moon, and therefore the Earth, was doing, say 4.2 billion years ago, that's probably about the time life first arose on our planet. We need to sample, find craters and date craters from much older parts of the moon, like the lunar far side, and that would tell us whether whether the impact flux on the early Earth, say 4.2 billion years ago, was low, which would have been possibly quite beneficial for early life getting started, or 100 times higher, which might have made it more difficult for life to get started. So this is understanding the impact flux on the early moon will tell us about the impact flux on the early Earth, and that will tell us about the impact environment under which life first arose on our planet. So that's something astrobiologists probably want to know. Moving on to the next thing, this photograph shows, it's another beautiful photograph. It shows the south pole of the moon. This was taken by Japanese Kaguya spacecraft about a decade ago, flying over the south pole of the moon from the far side towards the near side. So obviously we have this beautiful Earth, full Earth in the sky here. For those of us who live in the northern hemisphere, it looks upside down because this is the south pole of the moon. So this is the continent of Australia here, where the laser pointer is, and this is Southeast Asia here. Anyway, the south pole of the moon is just about there, where the laser pointer is presently, on the rim of this 20-kilometer diameter crater that is called Shackleton. But the point here is that the sun is always low in the sky at the lunar poles, and so there's a lot of shadow in this image. And these craters, like Shackleton here, the sun is so low in the sky that the bottoms of these craters, the floors of these craters, never see the sun. And this means they're some of the coldest places in the solar system. Certainly the coldest places in the inner solar system, with temperatures of about 40 Kelvin, or even 20 to 40 Kelvin. And under those temperatures, water ice is stable. And there's now quite a lot of circumstantial evidence that water ice is collected in permanently shadowed craters at the poles of the moon. But this water will have come from comets and from asteroids, and these will have delivered water and other volatiles and maybe organic materials to the moon. And so by exploring these ices in these permanently shadowed craters, we'll have a record of the rate at which comets and meteorites have delivered water and organic materials to the moon. But this will be the same, more or less, as the rate at which comets and asteroids have delivered water and organic materials to the Earth. So that's important for understanding how the Earth got its water and its volatiles and became a habitable environment, so in its earliest history. And the moon may have preserved a record of this. The next point on my list was the idea that we might find meteorites from the Earth preserved on the moon. And this seems quite likely because we have meteorites from the moon on the Earth. And these are meteorites that are launched into space by other big giant meteorite impacts. And some of the ejecta goes flying into space and can travel between planets. We also have meteorites from Mars on the Earth. So it's possible that we find meteorites from the Earth on the moon, dating from the Earth's earliest history, earlier than the Earth's currently oldest rocks. So since we think life arose on our planet about 4,000 million years ago, We'd very much like to know what conditions on the early Earth were like 4,000 million years ago, but the Earth hasn't preserved any rocks of that age. Not, at least we haven't found any yet, because the Earth has destroyed them all through erosion. So early Earth rocks might be found on the moon, and if we can find them on the moon, they would contain a record of what the Earth's surface environment was like at the time life first arose on our planet. Which would be a useful thing for astrobiologists to know. So this photograph, this is Buzz Aldrin's boot. This is from Apollo 11. And there's a rock here just in front of his boot. Now, this will just be a moon rock, of course. But some such rocks, a small number of such rocks on the moon, if we could find them, might be meteorites derived from the early Earth, containing a record of the Earth's earliest geological and perhaps also biological history. And so they would be very valuable samples to find if we could find them. The next thing on my list was a record of astrophysical processes relevant to life on Earth. So obviously the Earth is a small planet wandering around a fairly ordinary star in the middle of the, well, not the middle, somewhere around the edge of the Milky Way galaxy. And we are therefore exposed to quite a lot of high energy cosmic processes which can affect and probably have affected the evolution of life through time. So two big examples. The picture on the left shows a solar flare. Every time we have massive flares on the sun, the solar wind is greatly increased in strength, and high energy charged particles, protons mostly from the sun, sweep through the solar system, where they can cause damage to biological, to living things, if there are any living things. They can also erode planetary atmospheres, which will make a planet less habitable than it would be otherwise. And so a record of the history of solar flares and solar activity through time would be a very useful thing to have. It would also, from an astronomy point of view, help us understand the evolution of the sun as a star, which is important for astrophysics. But for astrobiology, understanding the history of the sun is important because the history of the sun will have affected life on Earth, but not only on Earth. If life ever evolved on Mars, activity in the solar activity in the past will have affected life on Mars as well, and also Venus. So understanding the sun as a star is important for understanding the habitability of the whole solar system. Then the picture on the right shows a galaxy, of course. So this is the Messier 51, the Whirlpool Galaxy. But I show this because our galaxy would look similar if we could get outside of our galaxy. And currently today, the solar system is in a pretty quiet part of the Milky Way galaxy. So if this was our galaxy, the solar system would be somewhere like there where the pointer is. But the solar system moves around the galaxy. It takes about 200 million years or so to move around the galaxy. So there will have been times when the solar system has been passing through spiral arms in the galaxy. It will have been close to exploding stars, may have passed through dense interstellar dust clouds. All of these are likely to have affected the habitability of the solar system, so the Earth, but also Mars and Venus, and maybe even places like Europa in the outer solar system. So we would quite like to have a record of how often has the sun passed through spiral arms? How often has the sun been close to exploding stars? Well, the surface of the moon, let me just go back to, well, this picture will do. The surface of the moon will record that because solar wind particles and galactic cosmic rays are implanted into the lunar soil. And if we sample that and extract these particles from it, we could build up a picture of the history of the sun as a star, the activity of the sun as a star, and also the changing galactic environment of the solar system. As the sun has orbited the solar system, because as the sun has orbited the solar system, the Earth and Moon have gone with it. But the Moon, because it's got no atmosphere and no magnetic field, that surface of the Moon has been totally unprotected from the space environment for all that time. So this is why I think the Moon is a good potential museum of the history of the ancient sun and also of the solar system's location in the galaxy. through the whole of solar system history, the last 4.5 billion years of solar system history. So I should just say that although we know the solar wind and galactic cosmic rays are implanted into the lunar soils because we've studied samples from the Apollo soils, like from Apollo 11 here, we know these materials are present. What we're currently lacking is a time-resolved record of this activity. Because if you were just to scoop up soil at, say, an Apollo landing site like this one here at Apollo 11, this soil has been developing on the surface of the moon for about 3.8 billion years. So we know solar wind and galactic cosmic rays are implanted into these lunar soils, but what we've extracted so far is just an average flux of solar wind, an average flux of cosmic rays over billions of years. Whereas what we want is a time resolved record so that we can know what the sun was doing or the galaxy was doing at any given time in the past. Well, fortunately, the moon's own geology can provide this for us. So if we imagine a geological process like erupting a lava flow on the surface of the moon, lava flow will develop. Then it will be struck in from space by micrometeorites and develop a regolith, a lunar soil. Then this regolith will be like a giant sponge, and it will soak up galactic cosmic rays and solar wind particles and perhaps more exotic things that fall on it from space. But then if another lava flow flows over the top, so this is panel 3 here, you'll see this I've called it a trapped regolith. So a regolith is a name for the lunar soil. So this regolith that was once on the lunar surface is now trapped underneath a younger lava flow, which means it's now sealed. It can no longer interact with the space environment. So if we were to find examples of such trapped, buried regoliths, they're often called paleoregoliths. If we were to examine such a trapped regolith, a paleoregolith, the solar wind particles, the galactic cosmic ray particles, the meteorite particles, all of them found within this trapped regolith, they would date from a well-defined interval of time between the ages of the older and the younger lava flow, which we could also date if we collected samples. Meanwhile, the whole process starts again at the top. So there'll be places on the moon where there'll be stacks and stacks of lava flows with trapped soils containing a record of ancient solar system history that we might be able to access. Picture on the right shows one such lava flow. This is in Mare Imbrium on the near side. I don't know whether you can see there's a sort of this tongue-shaped feature here is a lava flow dated to 3 billion years old, but it's gone over the top of an older lava flow, 3.3 billion years old. So trapped between the two of these, if one was to, where the laser pointer is now, if we were to drill down, it would be about 50 meters deep. Drill down where the laser pointer is now, you'd go through this lava flow on the top, and eventually you'd reach a layer trapped between the two. And in that layer, there would be an ancient lunar soil, and it would tell us what the sun was doing 3 billion years ago, what the galaxy was doing 3 billion years ago, what meteorites were hitting the Earth-Moon system 3 billion years ago. This is just one location. There are places on the moon where there are many other such potential locations. So if we could explore enough of these places, we'd build up a history of the ancient sun and the solar system's place in the galaxy, which would be of interest to astrobiology, also interest to astrophysics, of course. Accessing these materials, though, will require a bit of effort because they will be buried. By definition, they will be buried. So it will require quite a lot of technology and quite a lot of equipment on the moon to access the subsurface. And it's one reason among several why I think accessing the record that the moon has for us of the early solar system is probably going to benefit greatly once we have people back again on the surface of the moon, because some of this exploration that's going to be needed is on such a large scale that I just am doubtful that small scale robots will be able to do it very efficiently, and having people on the moon would probably greatly help. Switching tack a little bit to another astrobiological reason for wanting to explore the moon, searching for surviving microbes and organic material on the sites of crashed spacecraft. So here's another nice photograph from the Apollo era. Nice crescent Earth in the background. This is the Apollo 11 lunar module ascent stage. So when this picture was taken, obviously by Mike Collins, Armstrong and Aldrin were in this lunar module ascent stage coming back. Once the Apollo astronauts had transferred back from their lunar module to the Apollo command modules, these lunar modules were crashed back into the moon. Partly they were crashed back into the moon to provide scientific data for the seismometers left on the lunar surface by the astronauts. So that's a geophysics experiment. But of course, because in each of these lunar modules, 2 people were living for 3 days without their spacesuit helmets on while inside the spacecraft. These spacecraft will have been absolutely full of microorganisms. Obviously, trillions and trillions of microorganisms went to the moon with each of the Apollo astronauts. Then these space vehicles were crashed back into the lunar surface. So the question is, whether any of these microorganisms managed to survive. Obviously, the lunar surface with no water, no atmosphere, high radiation, it's a very difficult place for microorganisms to survive, and maybe they haven't done. On the other hand, they would have been slightly protected because they would have been inside the crashed remains of a spacecraft rather than exposed on the surface of rather than exposed directly to space. So we could learn a lot about how microbes survive in the space environment by visiting some of the crashed sites of spacecraft, especially the Apollo spacecraft, on the surface of the moon. If we were to visit these places, take samples, we would see whether life had survived for 50 years in these really harsh conditions. But even if the microbes that were certainly landed on the moon, even if they didn't survive, we would be able to learn what kind of organic molecules they have decayed into. And this might also help inform our strategies for searching for life elsewhere in the solar system. Right, I'm coming now, since I've only got 10 minutes left, to perhaps the most exotic, potentially the most exciting, but perhaps the most strange astrobiological reason for wanting to go back to the moon. So at this point, you may think I've gone completely mad here. I started off with talking about stuff that was quite normal science and quite prosaic, like calibrating meteorite impacts. And then I've gone through a whole load of other astrobiology reasons for wanting to explore the moon. And I've ended up with this exotic possibilities, searching for alien artifacts. Now, before you think I've gone completely mad to mention this, I just want to set the scene a little bit. What I'm not really talking about is the kind of thing you can see in this picture. I don't know whether all of you have seen the Stanley Kubrick's movie 2001: A Space Odyssey. If you haven't, then I recommend it. Where a large alien artifact, namely this black obelisk, was found on the moon by astronauts working out of a lunar base. They discovered a strange magnetic anomaly. They dug down. They had to dig a trench, as you can see, and they found this, and it was clearly an alien artifact. And if we found anything like that on the real moon, I mean, obviously that would be probably one of the most important scientific discoveries ever in human history. And probably that's not very likely. But there is another possibility for searching for alien artifacts on the moon, which I think is a little bit underappreciated. It's this argument. I'm sorry for all the words on this text on the slide, but I'll talk you through it. The basic argument here is due to a Ukrainian astronomer called Yuri Arkhipov, who first published this idea in about 1998. And I think it needs to be taken much more seriously than it often is. So Arkhipov's idea was, you don't have to imagine I mean, obviously, if we were to find a big alien artifact like this 2001 obelisk on the moon, it would mean the aliens had come here. It would mean that they'd solved the problem of traveling interstellar distances, which would be a very high, hugely expensive, difficult undertaking. Probably not impossible to a sufficiently advanced civilization, but probably really difficult undertaking. But Archipob's point was, you don't necessarily have to build an interstellar spaceship. You don't have to build a starship in order for your artifacts to travel between the stars. Because if you're doing any activity in space, then you're going to generate space debris. And some of this space debris is going to start drifting out between the stars. So consider, for example, a society that might be like ours in 100 years' time, or maybe 50 years' time, where we have decided that asteroids contain economically useful materials, so we start mining asteroids. So here's an artist's impression of some asteroid miner at work. Any civilization that starts mining its asteroids or developing its own solar system, even if it doesn't leave its own solar system, will develop space debris, which will eventually get pushed out into interstellar space. So this is the second point. Even without a deliberate program of interstellar travel, much of the debris produced by a spacefaring civilization will get pushed out into space by the radiation pressure and the solar wind of its star. So that, at least the small particles will, and they'll be like micron-sized particles being blown out from stars by the solar wind and the radiation from the star. Of course, larger artifacts may also get ejected. So we ourselves have used the giant planets to accelerate some of our spacecraft, like the Voyager spacecraft, also the New Horizons spacecraft. These spacecraft are leaving the solar system because they've had gravitational swing shot effects from Jupiter and Saturn. And if we put enough spacecraft into the solar system, then eventually some of these space debris will get ejected out into interstellar space as well. Anyway, the point is, Archipob's point was, here's a picture of a galaxy again. So suppose it's our galaxy. There may be, and there may have been in the history of the galaxy, spacefaring civilizations that evolved on, who knows, some stars somewhere in this galaxy. These civilizations may now all be extinct, but they may, if they'd spent several hundred years or thousands of years mining their own solar systems, they would have generated space debris, which will eventually get pushed out into the spaces between the stars. So the point is, the more technological civilizations that have ever existed in the history of the galaxy, the more interstellar space debris there will be. I think that's fair to say. And the more interstellar space debris there is, the greater the chance that the surface of an airless body like the moon will collect it. Bear in mind that the moon and the solar system has been around our galaxy 20 times since the solar system formed. So the more technological civilizations there have been in our galaxy producing space debris, the greater the chance that over the last 4 billion years, as the solar system has orbited the galaxy, the greater the chance that some of this would have struck the surface of the moon. Would have just struck the surface of the Earth as well, of course, but probably been washed away and buried or eroded away on the Earth, because the Earth is such an active planet, whereas the surface of the moon may potentially have preserved it. So this is a very exotic possibility. I'm not telling you that we should search them. That this should be our main reason for exploring the moon. Our main reason for exploring the moon should be all of these other reasons. All of these are good scientific reasons wanting to explore the moon of interest to astrobiology. But if we're going to explore the moon anyway, for all of these reasons, we might just want to keep at the back of our minds Archipob's argument that we might actually find exotic materials in the moon, on the surface of the moon, that we weren't expecting, in the form of artifacts produced by alien civilizations in the history of the galaxy. And that, of course, if we were to detect those from an astrobiology point of view, this would be one of the most important discoveries ever. I mean, I personally think the chance of that is really low, but that doesn't mean we shouldn't look. Okay, so I'm coming to the last couple of slides now. I should just say that I've tried to give here what I think are astrobiology reasons for wanting to explore the moon, but I don't want you to think that astrobiology is the only reason or even the main reason for exploring the moon. There are lots of other reasons for exploring the moon, scientific reasons. Obviously, if we explore the moon, we'll learn a lot more about the moon's geology and its history, and some of that is of interest to astrobiology, but a lot of it is also interest to geology and to planetary science. The moon's surface is also a potentially useful platform to conduct astronomy from. So here is an artist's drawing of an observatory on the moon, especially radio astronomy, and especially from the far side of the moon, because the far side of the moon never sees the Earth. It's totally shielded from artificial radio noise from the Earth, which makes it a very radio quiet location from which radio astronomy could be conducted. Of course, some of that radio astronomy could be SETI. SETI is a branch of radio astronomy searching for extraterrestrial intelligence with radio waves. And this too is an aspect of astrobiology that would benefit from exploring the moon. But then there's also a lot of astrophysics that would benefit from radio astronomy conducted from the moon that's got nothing to do with astrobiology. So that's another scientific reason for wanting to explore the moon. I haven't talked about it because it doesn't relate to astrobiology, but it is another possible reason for wanting to explore the moon. In addition to mining asteroids, we may find that the moon contains economically useful natural resources that might be of use to the future of the world economy. I don't think we know that yet. That's why I put a question mark. We haven't really explored the moon enough to know whether it will be economically useful or not. But we won't know unless we do explore it. So it is another reason for exploring the moon. And then finally, as I mentioned at the beginning, if we explore the moon, we'll learn a lot of techniques and gain a lot of experience and develop a lot of technology, which will be helpful if we want to explore other places in the solar system, especially the planet Mars, where there are even stronger astrobiological reasons for us wanting to explore. So it's therefore quite good that it looks like humanity is going to start exploring the moon again in earnest early this century. Obviously, the US is kind of leading this with its Artemis program, and this is a NASA graphic, but also China and Russia have expressed interest in sending people to the moon. The Chinese program is certainly very serious, and I fully expect them to do so. So it looks like humans will be going back to the moon in the coming decades, and I guess the point of my talk here is that if we do so, obviously we'll learn a lot of science, and some of that science will be of interest to astrobiology. I just want to make one final point, and this is my final slide. Two points, really. The first thing is, I mean, it will be great to have humans back on the moon, exploring the moon in person again. But I think some of the things I talked about are going to require an exploration, a level of exploration that probably greatly exceeds what can be done with Apollo style missions, where spacecraft lands, some people get out, they do some science for a few days, and then they return. A lot of what I've talked about would require building up a bit of infrastructure on the moon. So I think really if we really want to understand what the moon has to tell us about the early history of the solar system, and hence much of that of interest to astrobiology, we'd benefit from building something like this. So this is an ESA graphic, obviously, and it's an ESA graphic of a moon base. I think the way to view moon bases is is to bear in mind the research stations that we currently have in Antarctica. So a lot of science is done on the continent of Antarctica. Biology, zoology, geology, astronomy, even astrobiology. But this science is climate science, obviously. The ozone hole was discovered in Antarctica. But the point is, all of this science in Antarctica is made possible because there are a small number of Antarctic research stations, Antarctic bases, that provide the infrastructure from which scientific investigations of Antarctica can happen. So I think the same argument would apply on the moon. Setting up an Antarctic-style base on the moon would provide local scientific infrastructure on the moon that would then support a whole range of different scientific activities. You know, it could support astronomers setting up a telescope. It could support geologists looking for Earth meteorites on the moon. It could support biologists looking for crashed spacecraft to see whether they still contain life. It could support drilling operations that would enable us to drill down into the deep subsurface. It might even allow us to discover alien artifacts if they exist. And doubtless it would enable scientific activities that we haven't even thought about yet. So I think the key reason for wanting to establish a permanent presence on the moon through a moon base like this is it would enable a whole range of scientific investigations, many of them of interest to astrobiology, many of them of interest to lots of different sciences. The other point I wanted to make there, just to come to an end, is I do think we need to try and work to make sure, if we set up a moon base and later a Mars base, hopefully, we've got to work quite hard to ensure that these are genuinely international endeavors. I mean, I don't think we want an American moon base, a Russian moon base, a Chinese moon base. I mean, this would be madness. What we need is a human moon base, a human Mars base, just as we have an international space station. So I think, I mean, this is a slightly political point, but I do think for those of us who are scientists who are interested in exploring the solar system for scientific purposes, we also should be doing what we can to try and ensure that this occurs as an international, global activity. Okay, thank you very much. I think I'll finish there. Thank you.
Sir, thank you so much for being here today with this delightful presentation. Now it is time for the questions. The first question is, to analyze activity of the sun, which aspects of moon soil are examined?
So it is the soils, the so-called regolith. If I go back to it's let me get my pointer. It is the lunar soils like this that we see Buzz Aldrin's boot print in, because it's these soils which are exposed to space and the solar wind is implanted into these soils. So obviously these soils are at the surface today. In order to understand the history of the sun, we need to find ancient soils that were exposed once on the surface, but are now buried. And so that would be the argument for drilling down through the surface to find these trapped ancient regoliths that will contain a record of the ancient sun, the early sun, and the galaxy that we probably want. So we have done lots of studies of the soil samples brought back by the Apollo missions 50 years ago. We've done lots of studies of that, which is why we know these cosmic ray particles and solar wind particles are present in these soils. But no one has ever yet studied any trapped, buried ancient soils. I mean, this is an argument for going back to the moon. We know where they are. We kind of know what we'd have to do. We know it's probably going to be quite hard work, some setup such as this. But all of that is for the future.
Thank you. The next question is there any way investigating at exoplanets up to date whether life is existing, or do we have to use some simulators and just experiment in Earth to find them?
So was that question about exoplanets?
Yes, anyway, investigating at exoplanets.
Yeah, so it's a very good question. I think there are two possible reasons why the moon can be important here. Obviously, we have now discovered many planets orbiting other stars. So these are called exoplanets. And this is one of the most exciting things that's happened in astronomy in the last 20 years or so. And we want to study these exoplanets to see whether they have life on them. But currently, it's very difficult to study these exoplanets because they're so faint that we get so little light from an Earth-sized exoplanet orbiting a star many light years away. We require very big telescopes to measure the light from these planets. So this is an argument for big space telescopes. Now, the big space telescopes don't necessarily have to be on the moon. But we probably do need big space telescopes. So we do need a space technology to build these big telescopes in space to study exoplanets. But then there is the question of how would we detect life on some exoplanet? I mean, the only tool an astronomer has would be to take a spectrum of this exoplanet and then look for spectral lines in the atmosphere of the exoplanet that are indicative, we believe, indicative of life. So this is where the moon can come in, because we do have one planet. This is why I've got this picture of the Earth here. There are proposals to put telescopes on the moon to study the Earth, pretending that the Earth is an exoplanet, because we know the Earth is an inhabited planet. And so if we can use that as a test case. We can pretend the Earth is an exoplanet, take spectra of the Earth with the kind of very low resolution, very low signal to noise spectra that we would get from a real exoplanet, and see whether we can detect life on Earth. Because then the argument is, if we can detect life on Earth that way, we could detect life on an exoplanet as well.
Thank you. The next question is, could solar winds have a direct effect on the creation of life?
That's a good question. I don't know the answer to that. I think most people who work in the origin of life field would say no. They would say no because most biologists studying the origin of life assume that life arose on the surface of the Earth. That's a reasonable assumption, of course. And the solar wind cannot reach the surface of the Earth for two reasons. Partly because the Earth has a magnetic field that protects us from the solar wind. But even without the magnetic field, the Earth's thick atmosphere stops the solar wind impinging on the surface of the Earth. So if life arose on the Earth, which it probably did, then no, the solar wind can't have had an obvious influence. But there is another slightly different aspect to this, and that's why I'll keep this picture of the moon, because I argued earlier that the craters like Shackleton crater here are cold enough for ice to be present, water ice and other ices, carbon dioxide, methane, maybe, frozen at these very low temperatures. These ices are exposed to the space environment, and they are therefore exposed to cosmic rays and possibly solar wind as well, which come in from space. And chemists have long realized that if you take ices, carbon dioxide, especially if you've got some ammonia or methane and water mixed in with, well, the ice is water, but if you have carbon dioxide and some nitrogen-bearing compounds mixed in with the ice, and then you irradiate it with high-energy particles like cosmic rays, you can produce organic molecules from these ices, because the cosmic rays, the radiation, drives chemical reactions that break the chemical bonds in the water molecules and the CO2 molecules, and then these atoms react to make more complicated molecules that are broadly organic molecules. And so these craters of the moon with ice on the surface, they would be a place to study the non-biological production of organic molecules through the interaction of cosmic rays with ices. And this could really be important for astrobiology, even if not for the Earth. Places in the outer solar system, like Jupiter's moon Europa and Saturn's moon Enceladus, these are also of interest to astrobiologists, and they have icy surfaces exposed to the radiation environment of space. And ice exposed to radiation can produce organic molecules. And we could learn about that process by seeing if such similar processes are going on in the interiors of permanently shadowed craters on the moon. I mean, obviously, it's a lot easier for us to reach the moon to study those processes than it would be to go to Europa, say, to study these processes. So I do think the moon could help in probably not the origin of life, but it probably could help us understand the origin of some organic molecules in the space environment.
Thank you. The next question is, if we base the story of the formation of the moon on the Theia-Earth collision, can we also think that microorganisms may have been transported to the moon from Earth and Theia?
Yes, so I think that's a good question. I think most people who've thought about this probably argue the Theia collision, the moon forming impact, was probably just far too violent. If there'd been any life on the Earth at that early time, probably it would have been extincted. I think the Theia collision was such a violent collision that probably by forming the moon, it will also have vaporized a large part of the Earth's crust and mantle, and on any oceans that the early Earth might have had would have been vaporized. It's really difficult to understand how any Earth life, if there was any at that stage, or even any Theia life, because who knows? The Theia object itself might have had life for all we know. But it's very difficult for us to understand how it could have survived that collision. On the other hand, after that collision, once the moon did form, the Earth has certainly been subjected to smaller meteorite impacts, but still quite large meteorite impacts, but smaller, which have knocked off chunks of the early Earth's crust, and some of these would have been launched into space. So absolutely, we might find early Earth rocks on the moon. They'd be younger than the moon and younger than the Theia collision, but they could still be really interesting because the Earth's geology, we have hardly any rocks on the Earth dating back older than 3.8 billion years ago. Really almost nothing dating back from earlier than 4 billion years ago. And yet the Earth is 4.5 billion years old. There's 500 million years of early Earth history where important things were probably happening, like the origin of life on our planet. And the Earth has not retained a geological record of that early window of 500 million years long. And yet meteorite impacts onto the Earth during that time may well have ejected bits of the early Earth that have landed on the moon where we may find them. So we haven't found any yet, but we should look, because there may be evidence, rocks from the very early history of the Earth waiting to be found on the moon. And this could tell us about what conditions were like on the early Earth at a time that life arose here.
Thank you. The next question is, even if we find an alien artifact, can we actually understand it is an artifact, since it does not have to be similar to our conception of artifacts?
Yes, I think that's a very good question, and it depends a little bit on what kind of artifacts we're thinking about. I mean, if we were to find something like this, then yeah, we wouldn't understand it, but we would probably recognize it as an artifact. But this is very unlikely, right? So Yuri Archipov's idea that we might find bits of space debris, the kind of artifacts he has in mind here would be tiny little particles, micron-sized particles that haven't really been created as an artifact. I mean, they're artifacts in the sense that they be artificially produced by some alien civilization, but not designed as artifacts. What he has in mind is like exotic alloys, say, I don't know, titanium, aluminium alloys that have been ejected from the rocket engines of some. So imagine some alien, suppose this is in an alien solar system and some alien spacecraft is mining its alien asteroid and it's got some rocket motor. Then every time it fires its rocket motor, part of the interior of the rocket motor that the rocket motor is made out of will get eroded from the engine and ejected out into space. So there'd be micron-sized or even tenths of a micron-sized little flecks of strange alloys. And eventually these would get wafted out into interstellar space and collect in the interstellar medium. That's his argument. And then the moon, as it goes around the galaxy all this time, might collect some of them. So the idea is we might find, if we sift through a lot of, sorry, it's the wrong slide, a lot of lunar soils, his argument is that we should keep a lookout for really exotic particles which don't look natural. They look technological because they're strange alloys. Then, of course, the question is, how do we prove that these are not Earth contaminants, right? There are probably a lot of these artificial artifacts on the moon now, thanks to all our human missions to the moon. So if we found a small fragment of, let's say, a titanium, aluminium titanium alloy or something, in the lunar regolith, obviously our first thought is this is contamination, space debris generated by ourselves. But I think there is an answer to that, because if you were then to look at the isotope ratios of these materials, I mean, metals in the solar system have particular isotopic ratios based on the conditions in which the solar system formed. A technology developed around another star, it might use the same sort of materials for its rocket engines. I mean, it might not, but suppose it does. Even if it uses the same sorts of materials for its technology, these materials, these alien metallurgists who built these things would be working with materials with different isotope ratios. And we could probably use that to determine whether an artifact is of alien origin or of terrestrial origin.
Thank you. That was all for the question part. It's our pleasure to have you here today, sir.
Oh, thank you very much. It's been a pleasure to give this talk.
Thank you. Dear participants, our second presentation will be in almost 15 minutes from now. Until then, please stay tuned and stay with us. See you in 15 minutes. Hello again. In this session, Armando Azua-Bustos will be here for his presentation. He is a research scientist of the Department of Paleontology and Habitability of the Center of Astrobiology of Spain. His work is focused on understanding how life adapts to extreme desiccation tolerance on Earth, and what can this tell us finding life elsewhere in the universe. Please ask your questions through chat box, because after the presentation we will have a Q&A session, and I will be delivering your questions to Mr. Azua-Bustos. Now, Armando Azua-Bustos is here for his presentation called Is Mars Too Dry for Life? Welcome, sir. How are you?
Hello. Hello, everyone.
The stage is yours, sir.
Okay, thank you very much. Thank you for the invitation. This afternoon, we are going to talk on whether there is enough water for life on Mars, and what that can tell us on the possibility of finding life elsewhere in the solar system as well. In 1976, two missions went to Mars with a specific objective of searching for evidence of life. This was the Viking 1 and 2 missions. They both went with a lander for the first time to the surface of Mars, and they undertook a number of experiments in order to assess whether you would have positive response from potential Martian life forms there. So this is an animation of the Viking lander. Both landers were the same, Viking 1 and Viking 2. They were able to take a sample of the soil around, and you have to mind that there are also rather superficial samples, no more than 15-20 centimeters of depth. So these landers took the samples, and then into the laboratory they were taking with them, and they undertook three critical experiments. The first one is the so-called paralytic release experiment, in which a sample of soil was incubated with a carbon tagged CO2 with the carbon-14, and having a lamp try to stimulate any potential phototrophic, that is photosynthetic microorganisms that could be found there on the sample. And then after that, the soil sample would be heated in order to turn any potential organics that were there, and then release them as a gas in order to detect them where any of these may have incorporated the C14 label from this label CO2 into any organic molecules. The second one is the so-called label release experiment, in which a browse of nutrients containing a number of simple elements like formate, glycine, a number of other elements were added to the soil as a dripping from a watery solution, with the hope again that since you already have all these nutrients labeled with carbon-14, if anything was metabolizing them and respiring, you would get again CO2 labeled with C14 in a response telling you that there was respiration by something in the soils. And the third experiment was the gas exchange experiment, in which again a broth of nutrients was added to the soil, and along a first step on first making the atmosphere of where the sample was contained humid in order to wake up any potential microorganisms there slowly, and then add nutrients again labeled in order to see where you have an imbalance or a number of gases there, and then see again if you could detect anything in terms of, for example, methane labeled with carbon-16, or a rise of oxygens or whatever. So the intriguing response was all of the three experiments were positive. You would have the expected response if something that was living in those soil samples. But this did not make sense when, in turn, those same soil samples were analyzed with a mass spectrometer that the landers were taking, able to measure the amount of organics, and they could not detect any at the parts per billion level. So it was thought, although there is an unanimous unanimous thought that this could be a negative response from the soil, saying, well, it seems that the samples of the Martian samples had something there that it was producing a chemical response, not a biological response that mimic life. But again, there are not a consensus on that, and we still are trying to figure out what happened with it, in particular with this experiment. So this brings us to the characteristic of Mars. Mars it has a very particular atmosphere. Almost all of it is CO2, just a few percentage of argon and also nitrogen and traces of other gases, which include water vapor and oxygen and others. And also it's a very thin atmosphere. It's just, if you measure the density of it, it's just 0.7% of the density of the atmosphere of Earth. This is a very thin atmosphere. Also, for the same reason, also Mars is a very dry planet and also a very cold planet. The mean temperature on any year on Mars is about -80 degrees Celsius, but you can reach easily at the poles temperatures of -125. But in the summer of Mars, because Mars also has an inclination similar to Earth, which means it has the seasons, at the equator, in a day, temperature can reach up to 20 degrees Celsius. But since the atmosphere is so thin, the dynamics there says that in that same day, when you reach 20 degrees Celsius during the day, in the night, temperature again drops to -73 during the night. So it's a very cold, very dry, and with a composition of an atmosphere which is almost CO2. So the thing about going to Mars is that it's very expensive. This is one of the last images sent by the Perseverance rover. The Mars 2020, which is the Perseverance rover, cost a little bit more than $2.7 billion. And the other mission that is exploring Mars now, which is the Mars Science Laboratory with the Curiosity rover, cost about a similar amount, $2.5 billion. So it's very expensive to send anything to Mars and very complicated as well. Even if you had the money, about 1/3 of the missions that have been sent by different countries to Mars have been unsuccessful. You can see the little red crosses, red X crosses here, telling you when those missions have failed, and the few that have been successful, and only in 1975, the first 2 missions sent by NASA, the Viking mission, were able to actually land on Mars. So it's not only expensive, but also it's very complicated. That is an advantage of having the possibility of trying to understand the possibility of finding life on Mars with what we call an analog model, a model that replicates some of the conditions, environmental conditions in particular, that Mars has, but much closer to us, as it is the case of the Atacama Desert in northern Chile. The Atacama Desert has a number of characteristics that makes it a very good analog model of Mars. First, there are regions in the Atacama Desert, because the Atacama is not homogeneously equal everywhere. There are regions of the Atacama Desert where relative humidity during the day easily reach 0.0, typically in the afternoon hours. Afternoon, about 2 or 3 p.m. typically. Any of the instruments that they've been taken there for many years, they are simply not able to measure any water on the atmosphere. The atmosphere is the driest on Earth, actually. This is explained by 3 main factors. First, the masses of air that are coming from the east, from the Atlantic Ocean, when they encounter the Andes Mountain, they deposit all the rain at that side of the mountains where Argentina and Bolivia are located. And when those masses of air are able to overcome the Andes, they become very dry. So you have an influx of very dry air coming there in the so-called rain shadow effect. Now, the rain shadow effect is common in other mountain ranges across the world, but this is one of the factors that explain the extreme aridity of the Atacama Desert. The second one is a similar environmental effect in which all the masses of air that causes all the rain that you have in the equator in countries like Colombia, etc. After they deposit those masses of water there, they go up really high in the atmosphere, and they come back again at the latitude where the Atacama is located. So you have an influx of a very dry mass of air coming from above that starts in a big cycle coming from the equatorial region. And also, you have the Humboldt current, which is coming from Antarctica, that as you can imagine, those waters are very cold. So you have little evaporation there, forming just a few clouds. When they form, they stop by the coastal range of the Atacama there. So you don't have any influx from anywhere from rains. That's explained why the Atacama is so dry for life. And also, it is that as the continent formed by plate tectonics by around 150 million years, the Atacama more or less always remain in the same latitude, so affected by the more or less the same environmental factors, which explain also that the Atacama is not only the driest, but also the oldest desert on Earth. Add to that in the Atacama, you can measure one of the highest UV radiation fluxes on Earth. This is the typical UV index scale you can see in almost everywhere, which is telling you when you have to protect from UV radiation in a scale that goes from 1 to 11. And it's typically 11 is considered to be extreme and beyond, where you have to necessarily wear sunscreen and protective clothing in order so you don't get sunburn. Well, in places like in the coastal, in the Andes Mountains of Atacama, but also in the high parallel core, we have measured UV radiations of up to 20. So it is really, really high, the UV radiation there. The problem with water is that when you remove it from an organism, the organisms die. Of course, you know that. And the way you measure how water is available for life, it's an index there that is called water activity. Water activity formally is the index of the partial vapor pressure of water in a solution, for example, a solution containing salt, divided by the standard state partial vapor pressure of water by water, clear water, with nothing but the pure water. An easier way to understand water activity is that if you measure the relative humidity in any environment and divide it by 100, that is water activity. So you have a water activity chart that tells you what happens with life as you lower the value of water activity. As I said, pure water will have a water activity of 1, meaning that water will be available for any life form on Earth. Most bacteria will stop growing and most of them will die if they are put in an environment where water activity is 0.9. There are about a few halophilic bacteria, the ones that are able to live in saline environments, that are able to survive and still grow at water activity 0.7. And there are just a couple of yeasts that are considered xerophilic. They like to live in very dry environments, that are able to still reproduce and grow at water 0.6, which, by the way, explains why honey, if you open a pot of honey in your kitchen, doesn't contaminate, because the water activity of honey is typically around 0.6, meaning that although you have all those sources of nutrients for microbial life, it is too dry for them. So nothing is able to grow on honey because of what is water activity around 0.6. But the question remains that we have seen a number of phenomena in the Atacama where water activity is much lower than that. So we just wonder, how is that possible to happen in an environment on the Atacama where you have water activity of up to 0, as I just showed you. So in the beautiful city of Ankara, for example, today, you will have a humidity of 35%. You can translate that to water activity of 0.35, and it will get high during the night, with a UV index of 1 in the scale of 10. Compare that to the city where I was born, in the middle of the Atacama Desert, in which at the same time today, you will have just 9% of humidity at the same time, where you're having that other amount in Ankara, which relates to a water activity of only 0.09. This is really, really dry environment there. And when you have an UV index score as extreme, you can sure bet that it will be much higher than 11. So that is a typical afternoon in the Atacama. So when NASA proposed how you should look for life on Mars, they said, well, a first step makes sense that let's go to Mars looking for those places where you have evidence of water, past or actual. And let's see there if you can find evidences of life. So I used that same approach in the Atacama Desert in order to say, well, let's try to, again, in this case, explore the Atacama and find for the evidence of water in different places and see how life is able to adapt to it. So I started in the coastal region of Atacama, going inland in order to see how life adapt to increasing aridity. One of the first findings was in the coastal cliff of the coastal range there. You can see these black bandings here. Those are biofilm, a collection of number of different microorganisms that there you have water activity that, depending on the time of the day, will move from 0.72 to 0.92. So it gets some quite high during the night hours, for example, and it will not get as low as 0.7 during the daytime hour, which explains that here life, microbial life, is able to survive exposed to the environment, the so-called epiphytic mode of life, where you can colonize the surface of rocks. Here we have found a number of different microorganisms representing the 3 domain of life, such as different types of archaea, bacteria, fungi, and we have been able to grow some of these species. In the same area, as part of a NASA project I participated a few years ago, we were trying to see if you could use infrared technology, infrared imaging in this case, in order to see if from afar you could detect cave entrances on Mars. So we first approached this hypothesis in caves of Atacama, which I know, and we proved that actually there were enough thermal difference in between the entrance of a cave from its surrounding in order to say, in the case of Mars, where you can use that technology in order to take cave entrances. But it was more interesting for me as a microbiologist to go inland and see if you could find photosynthetic life inside a cave. And amazingly, at the very bottom of a cave, I found these beautiful green biofilms, and I took samples of them. And here, water activity starts dropping down. Here in the cave, you can see the water activity get to 0.5 or something in the low range. Here, we found in this green biofilm a new type of microalgae from the genus Cyanidium that was able to survive at the very bottom of the cave, well protected from UV radiation, but close enough to the cave entrance in order to receive enough light, which is about 0.06% of the amount of light you have outside. And with that little amount of light, that microalgae was able to photosynthesize. In a similar cave, but south in the coastal region of Atacama, this is a much bigger cave in this case, we found a very different phenomenon. Here just a few steps from the entrance, by the way, you could find something green growing not on the cave walls, but on top of the spider web that covered the cave walls. So it was a fascinating question to try to answer, well, why this, which seemed to be something that is making photosynthesis, thus the green color was what would like to grow on top of the spider webs, not the cave walls that in the cave entrance. Here now we just went a view like 20 meters inside the coastal range and see how water activity start dropping really fast to 0.14. You can see here these green things growing on top of the spider webs, and we understood that this, because we found there was a new type, also another type of microalgae. It was surviving here because the filk of the spider web is quite hygroscopic, so it was able to trap the water from the low cloud that were affecting this area in order to trap water. So we came back, and then this time at 3 a.m. in the morning, and we could actually see the same spider web covered by little droplets of water, telling us that this species was able to use water condensing on the spider web as a source of water in the course of the driest desert on Earth. It has adapted in a most fantastic way in order to trap water from the environment, using as little nets the spider web that cover the cave entrance. Why these findings are interesting? Because we do know there are a number of cave entrances on Mars, representing who knows how big caves inside. So what we showed that with our analog model of caves on Atacama, what could be happening on Mars, as I said, that you could find things enough protected from the UV radiation, which in the case of Mars goes unimpeded to the surface because it doesn't have it have little amount of oxygen, so it has almost no ozone. So even the most dangerous UVC radiation is able to reach the surface of Mars. So you will have enough protection from being enough inside the cave, protected from the outside environment, but close enough in order to get a little light still in order to, for example, do photosynthesis. So that was an interesting finding. Here on Earth, life has already created the ways in order to survive inside a cave, for example, using different wavelength of the light. So, for example, when using visible light, life is able to, when I say life, I'm always referring to microbial life. It always is able to use chlorophyll A for that purpose. If you go to the twilight zone, you can start getting into the infrared spectra. You can use chlorophyll F for that end. And when you go into really the infrared spectra, and on the very long wavelength, you can use chlorophyll D. So life has already solved the way to use little amounts of light and different type of life if you're living inside a cave. As I said, this is a cave entrance that we know that this is one of the cave entrances we know there is on Mars. We think actually though these are the skylight of lava tube. That is portions of the lava tube here that have collapsed, letting light to go inside. This also happens in the case of the moon. We know that some of these entrances are quite big. And given the characteristic of the moon and Mars being much smaller and its relationship with gravity, we think that some of the caves on Mars and also on the moon must be even larger than the largest cave on Earth. This is, if you can see, there's a few people sitting there in order to see the scale of this particular cave on Earth. So, for example, this cave in the moon, we have estimated that it could contain easily a few cities inside. And this is mind-boggling because we are also developing the technologies in order to explore the cave of Mars and on the moons. In the case of Mars, for looking for evidences of life, which will be highly dependent on the new robot that will explore the red planet using artificial intelligence, mainly in order to explore and characterize a very difficult environment. It's not the same thing that, you know, driving a rover on the surface or trying to go and then explore a cave in order to take samples and see if we could actually prove the hypothesis I just mentioned. So those technologies are already being tested. In the few decades, next decades, we hope that we'll be exploring the first cave on Mars or on the moon. Actually, when we think about colonizing the moon and Mars, we think that maybe the first colony will use caves because it is already a protected environment where you can build your first moon station or your Mars station. Here you have the big factor that you can protect yourself from radiation. You can even think about maybe closing that cave in order to create an artificial atmosphere, for example, as well, or better manage the temperature. So for me, it's amazing thinking that when thinking about exploring with the technology that we have now, when thinking about exploring the Mars and the moon, we're coming back to our great-grandfathers did in the past, using caves as a way to adapt to difficult environments. Now, continuing our route inland into the Atacama, once we leave the coastal range of the Atacama and start exploring what you can find in the hills around, there's a different phenomenon what tells you what life does when confronted with increasing desiccation. Here, life still depends on the cloud that cover those areas. So fogs or clouds, low clouds are the main source of water. And if you inspect rocks like quartz, you can see that you find this beautiful green high polytic biofilm, meaning that the biofilm that you can find below rocks like this. You can see them here in detail, and then when you see those green colors again, you can again suspect that you have something photosynthetic living under those quartz rocks. Here again, you can see that although again water activity typically during the nighttime hours it can get to 0.9, again during the day it can get really low to 0.16. And the nice thing about quartz stones that are able, most of those quartz stones are translucent to the photosynthetic active radiation, which is a range that is able to be used by photosynthesis by microbial life. It depends on the rocks. You will have more or less light under them, but if you have light and if you have water, you have the main components, and of course the CO2 of the atmosphere, you have the main component photosynthesis. But also we discovered that the quartz zone remain much colder than the environment. So it seems that they preferentially accumulate water during the nighttime hours, and they keep it longer during the day to stimulate the colonization of microbial species below the quartz. And under any of these quartzes, the colonized quartzes, you will find at least 70 different types of species representing again the three domains of life, meaning cyanobacteria, bacteria, archaea, and a few types of microalgae. So they constitute really little island of biodiversity. You will have a very stressful environment, but if you pick up the proper rock, in this case the quartz rock, you will find life under them. A similar phenomena in this area happens with what I'm showing here. This is gypsum, calcium sulfide. And if you crack those exposed gypsum rocks, you will see that a few millimeters below the surface of the gypsum, you will get to see this green color, telling you that you have something photosynthetic. And actually, other colleagues, this last species in mine, have been able to isolate both microalgae and cyanobacteria living just a few millimeters below the gypsum surface. Then we go to the hyperadic core of the Atacama, the place I told you that you typically would find water activity in the range of 0 during the day. This is a particular place. Yangai was proposed and discovered by NASA as the driest on Earth. I was just an observer of those missions when this research took samples from different institutions, but led by NASA. When they proposed that this place, it was interesting. And what I did, they replicated several of the experiments that were undertaken by the Viking mission, that they found more or less the similar results. So in 2003, they formally proposed that the Atacama Desert could be a good analog model of Mars, and maybe, at least in Yangai here, it could be the right limit for microbial life. I mean, the Yangai could be too dry for life as we know it. So what they said, they could not, I mean, they could find organics, but at trace level, they could find a few culturable bacteria. They could not recover DNA from its soils. And as I said, when they repeated some of the Viking experiment here, they more or less found the same response, saying that there was something in the soil that was creating a false positive. And they said that this particular site, Yangai, may be the right place on Earth. Now, we have to consider that when NASA did all those experiments, they were working here, but if you would expect that a few kilometers south, which is here, you would see that these are halide crystals, almost composed of 99.9 sodium chloride, the same salt table used for cooking. And you would see that these halides, many of them would contain these gray bandings. And if you look inside, you find a number of types, again, cyanobacteria that were able to live inside the halide. So Yangai, as I knew well, because I knew that area before, wasn't as dry as what it was supposed to be. So having my experience, again, living in Atacama for more than 20 years, I try to remember the places that were never see or few or almost never saw any clouds, where I didn't remember seeing any fogs, and also the places that were very windy, because due to evapotranspiration, wind is a strong driver of that. When you have a windy place, it takes easily all the water from the environment and any living thing that you have there. So this allowed me to find 3 other sites, with the driest being Maria Elena South, where here water activity again dropped to 0 in the afternoon hour, but during the nighttime hours or during the afternoon hour, it wouldn't get higher than 0.58. And actually, this one was the driest place on Earth, and of course, the driest of Atacama. And the question here is that, could we find anything living here? When we put our sensors in the soil profile, we could find that at around about 50 centimeters down, water activity was permanently in time 0.07. It didn't vary much. It was always more or less the same, 0.07. That was actually the driest areas of the Atacama. Again, as I said, for the first time, we could find a place that was as dry as Mars. When we compared our data in those years with the same data was being produced by the Curiosity rover on Gate Crater, our values match the lowest measured by the Curiosity rover as well. So we could for the first time say, well, we have found a place that is as dry or sometimes even drier than Mars. So the question here was, well, have we found the dry limit for life on Earth? Have we found a place so dry that nothing is able to survive on it? And I'm speaking about the subsurface of the soil. To our surprise, when we took different samples up to 1 meter of depth, we could find a number of different microorganisms that we're trying to understand how is that possible, how these microorganisms are able to survive in a place that has such a low amount of water. Just 3 species were able to find, and here at different depths, but we could that we saw it was too dry for life. Changes then came that told us also of the amazing adaptation of microbial life to these extremely light places. This started in 2015 when we were driving to this site, Maria Elena, and we started noticing this small lagoon beside the road. So we stopped, took a few pictures, and we didn't think that it was caused by a natural cause. But actually, in 2017, this repeated again. And I have to say here that in the Atacama, it does rain, but at the foothill of the Andes, when once a year, typically in the summer, some of those clouds are able to go inland into the Atacama, but only the foothill of the Andes. So that explains in that area, and only that there in that area, you have an ecosystem like this one, where you will find different type of animals and plants, etc., which is quite different from the place of the hyperarid cold Atacama, which I have just been showing you, right? So it's a completely different environment. But what happened in 2015 and also in 2017 and then again in 2019 is that masses of air with a huge amount of cloud came from the other side, that is from the Pacific Ocean, as never recorded ever before in the meteorological history of Chile, which is it started in the 1500s. So we have a long meteorological record there. Never has something like this with masses of air coming and causing rains in the hyperarid Atacama, as it happened in that case, which causes these lagoons again, but in Yangay, actually, in the place that was proposed by NASA to be the driest. So no one was ever saw that we would see something like that with a small water lagoon in one of the driest places on Earth. And the question is, well, we saw that water here will be welcomed by life. We saw that these places were so dry that if you add them water to them, you will see zillions of species growing there in the water. But amazingly, we could only see 4 types of different microorganisms in the water by mass sequencing. Only 4 types of microorganisms in the water, which agreed with the top 4 type of morphotype that you could see by morphology. And the thing is that, well, the question is, what happened with all these species that have been described in Yangay before, around between 50 and 100 different species in the soil? What happened with all those species? When we compare those 4 species of the water with the soils, we could see that 85% of the species there were not anymore in the water of this lagoon. And I think what's going on here? What we think is here that these microorganisms are so highly adapted to little water. When you add too much water and too fast, they die from osmotic burst. They simply do not deal how to live with so much water. How we think that was what happened there? Because when we analyze a number of biosignatures in this site, we could see, for example, a molecule like this one that is a typical compound that is telling you about the active synthesis of lipids that compose the membrane of different microorganisms. But we could also see, for example, with this I mean the 4 types of bacteria we could find in the water, but we could also see molecules like pristine and phytane, where a typical degradation product of chlorophyll. But we could not see any photosynthetic microorganism, not by next generation sequencing, not by culture, not by morphology or any other method. So we think that we were seeing what the molecular remnant of those species that were not able to adapt to the water. And with this, I mean the cyanobacteria that were living in this halite, given that it's sodium chloride, they were dissolved by these rains. This also caused in this area that and this is a hypothesis we're still testing, that we think that this rain replenish the water table below the surface here, providing then in the long term a source of water that came from below. And we found this clay layer composed of smectite, a particular type of clay, just about 30 centimeters below the surface. And here, as opposed to the water activity that you remember I mentioned in the case of Maria Elena, when you go into the subsurface, you will be as low as 0.007. Here, the clay layer had a water activity of 0.78, and that made a complete difference, because there you have water for life. In this case, as a wet layer of clays, which explains why we could able to find all these microorganisms living there, including bacteria and archaea being the different gray shades that I'm showing there, being able to survive from the water that was trapped inside those clay layers. And we were able again to grow many of them. And the interesting lesson here that this was happening just a few centimeters below the surface on one of the driest places on Earth. And this was a very interesting finding, because it tells you that you can't just simply say this place is too dry for life unless you explore it completely, because in this case you just need to drill, as the ExoMars mission will be sent by the European Agency, the Space Agency will be sent in 2022, will go with the precise end to look for evidence of life in this surface based on findings of what we have seen in Atacama. So, to summarize, see that when we are in the coastal range of Atacama, where you have enough water for life, with that I mean water activity between 0.7 and 0.9, life can still be found exposed to the surface, living from photosynthesis as the main source of energy, and then a number of other heterotrophic associated bacteria. If you go just a few kilometers inland, then life must find a refuge, some place to protect itself. In this case, below quartzstone, because water activity during the day will drop as low as 0.1. If you go a little bit inland again, you will have to go into the rocks in order to protect yourself in the endolithic mode of life, because water activity can get as low as zero. But if you go into the really dry places inland in the hyperaric core, you have to dig yourself into the underground in order to survive. And again, this is a very interesting lesson, because we think that Mars was a much wetter planet in the past. So we think that this is the evolution of life that may have taken place there, where you could find epiphytic life when it was in the wet phase. Then you have to find life to protect yourself when it was getting drier in the hypolytic mode of life. As it was getting drier, you have to go endolithic. And nowadays, what my findings tell me about Atacama is that you have to look for evidence of life in the underground. And also an interesting lesson in the case of the Atacama is that tell me what epoch of Mars you're interested in, the past or the more recent epochs, and I will tell you exactly to what place to go into the Atacama to try to understand that particular period of Mars. So I cannot tell you exactly what you will find on Mars, but I can tell you what to look for evidences, for example, inside caves or under the ground, and it will be very likely you find something if you have a source of water, and we found in this wake place. And even in the place where you don't find any evidence of the water at all, I have shown you that there are places in Atacama you can still find evidence of life. So the search for life in Mars is still ongoing, and we simply still have to really explore it well in order to see where is an inhabited planet or not, because we know that Mars is a habitable planet. It has all the conditions, more in the past than now, in order for life to start. We just simply don't know. We don't know what happened with the life, with that life if it ever originated there. But at least with my research, I can tell you, as I said, where to look for evidence of life from Mars, and where to look for in order to do that. And with that, I done. Thank you very much. Questions, comments, welcome.
Thank you so much for this delightful presentation, sir. Now it is time for the questions. I will deliver your questions to Mr. Azua-Bustos. The first question is, putting aside the possibility of being dry, it was suggested that last month rivers and oceans disappeared because Mars was too small to hold water. What do you think about this?
Could you say again the question, because the last part I couldn't hear well.
I'm repeating the question.
Yeah.
Putting aside the possibility of being dry, it was suggested that last month rivers and oceans disappeared because Mars was too small to hold water. What do you think about this?
Actually, that's a very interesting question, because we still are not sure how much water do we have on Mars. As you remember, we do know we have water because the Phoenix lander, when it goes to the poles, it just has to scratch a few centimeters of the surface to find a big block of ice, or water ice. So we know that water is there. We know there was a lot of water in the past, as the question says, on the many evidence of having oceans and rivers. But there are also studies that suggest that up to 85% of the Martian surface has ice below it. So we still are not sure of the amount of water for life available, and we are still looking for that evidence. And I think the ExoMars mission that will be sent to Mars in 2022 will have a say on that, because it will have a drill that go into the subsurface in order to see how dry the surface ice is when you drill in different places, right? So we are not still sure about how much there is water. There are also a number of evidences in the walls of many craters where you see something that looks like water running down, typically by the end of the spring. So we do have evidences. We do think that you may have water as ice. Depending on the season of Mars, you could even have liquid water in very particular conditions. So this is a very still yet to be resolved question.
Thank you. The next question is, if we compare Earth and Mars, Mars is more vulnerable to radiation coming from the sun. What are the possible advantages and disadvantages of this?
Well, for life, it's a completely disadvantage, right? Because in the case of Mars, I spoke about UV radiation, but also you have to consider the more dangerous ionizing radiation, like X-rays and gamma rays, and all kind of radiation coming from space. On Earth, we are protected because we have a magnetic field created by our iron nuclide that is turning and creating this magnetic field, right, that stop all the most dangerous radiation. In the case of Mars, it seems that its iron nuclide already stopped, so it has no or very small or very weak magnetic field. So all those very dangerous radiation again are able to get completely unimpeded onto the surface, and a few also centimeters, or depending on the radiation, even more below the surface. So that's why again we think that if you find evidence of actual or past life, the remains of life, you have to go into the surface in areas that may have been more protected by different type of radiation, and that also includes caves, right? If you go deep enough inside a cave, again, this is a protected environment, and then for life and also for us. And that's why we think that we are going to colonize Mars first by inhabiting caves, again, trying to solve the problem of radiation.
Thank you. The next question is, are there any studies conducted in order to grow plants on Mars?
No, we have to be very clear there have been a number of simulations, and depending on the simulation, they are well done or not. I have seen very crappy simulations. First, we have to clarify Mars. Actually, although I spoke about soils, it doesn't have soil, because the soil is the mineral component plus the organic component that we have on Earth. All kinds of microorganisms, roots, little insects, everything living. If you add to the mineral phase, then you have the soil. In the case of Mars, at least up to now, we don't have any evidence of the organic component or the living component of soil. So you have to call about the regolith. Actually, the regolith is only the mineral phase of which we refer by simplicity as soil in the case of Mars, which you always say the Martian regolith. Now, there are a number of ways to replicate the Martian regolith here. There are a number of different similants of that regolith. Many studies have been using regolith that still have some organic. So if you grow things on those analog that are typically coming from environments, for example, there's a very famous analog environment used for decades, which is the JSC1, proposed by the Johnson Space Center. That is not difficult to grow their plants, but if you simulate by adding a list of the chemical constituent of the mineral we have found in life, and you try to grow plant away, they all die. I mean, I have done the experiment by myself in my laboratory. But then again, you have solved just one problem. If you come up with a way to use the Martian regolith, you have to really change it in order to make it amenable for plant growth. But you haven't solved everything. You need a source of water. You need a source of light. Probably you will never be able to grow plant on the surface, because again, if you even think about a greenhouse, how do you protect it from the radiation I just told you? Probably we have to create greenhouse, but again, maybe hidden in caves or something like that in order to protect them. So it will not be easy. And there is again a number of experiments that do not reproduce properly the conditions in order to say whether we can use the regolith or not on Mars. If you do, but we do know that you use this mineral mixture representing the typical Martian regolith, everything dies on that. You have to really change it in order to make it similar to a soil.
Thank you. The next question is, even if we find life on a cave of Mars, what would it be like?
That's a very intriguing question. Well, for me, it's very easy. There's just two possibilities. That whatever origin that took place on life on Mars was so different from Earth that it has a different constituent. It's a different type of life. Or that the chemical basis of whatever origin of life you had on Mars is similar to Earth. And actually, there are some say that if you consider the transfer of material from Mars to Earth, there's quite a lot of transfer of material through the geological ages, right? And we have estimates about 30 tons of Mars arriving to Earth every year. Most of that, or it's more the particles or pieces that burn in the atmosphere, we never know about it. But at least we have around like 25 confirmed meteorites that have come from Mars. So that gives you a little bit about statistics, and also a transfer from materials from Earth to Mars. Just think about the last impact event we had 65 million years ago that extinguished all the dinosaurs. In that impact, huge chunk of Earth went to space. So 65 million years ago, you have 65 minutes in order for part of that material to have arrived to everyone in the neighborhood, the moon, Mars, etc. So if we don't find evidence of life in a Martian cave, so to speak, and the chemistry is the same, is that one contaminated the other. And some say that it may have happened that in the past, when life was originated on Earth, the conditions were really good also on Mars. It could have happened, amazingly, that life may have originated on Mars and then transferred to Earth and colonized here. And we will know that if the chemistry, for example, is the same. So we're looking for Martians, and we just need to look into the mirror in order to see the nearest Martian, right? Or the opposite. So the thing there will be, if we find evidence of life and compare them in order to see how different they are, in order to see they have you have two different origins of life or not. If they are very similar or identical, we could say that something went as described, I just described, in order to understand that possibility as well. That would be a very intriguing question. When we find something, how similar do we know on Earth it is?
Thank you. That was all for the question part. Sir, thank you so much for being here today with us with this amazing presentation. It was a pleasure to have you here today.
Thank you very much for the invitation and the attendance. Thank you very much, and bye to everyone.
Bye-bye. Dear
Bye.
participants, now we have a 15-minute break. After the break, David Deamer will be with us with his presentation. Until then, stay tuned and stay with us. See you in 15 minutes. Hello again. In the last session of second Astrobiology live presentation series, David Deamer, a research professor in the Department of Biomolecular Engineering at the University of California, Santa Cruz, will be with us. Mr. Deamer studies how the first cellular life appeared on Earth, with his projects related to organic carbon compounds in meteorites and how self-assembly of complex lipid structures could have been involved in the origin of life. Please ask your questions through chat box because after the presentation we will have a Q&A session. Now David Deamer is with us with his presentation called Where Can Life Begin on Habitable Planets? The Hot Spring Hypothesis. Welcome, sir. How are you?
Thank you. Are you able to hear me now?
Yes, sir. We hear you clearly.
Good. I'm glad. Thank you for the invitation to tell you about some of the research we're doing. Life, everybody knows, requires liquid water. And in fact, as we search for life on other planets, the question we ask is whether there was liquid water available. But it's more than just liquid water. There are two kinds of water on our planet, and that's today. We have salt water and fresh water. And on the early Earth, we think that there were also fresh water and salty water available. And I'm going to show you why I think that. So today we have hydrothermal vents, and that has been proposed as one possible site for life to begin. There are two kinds of hydrothermal vents. One is the so-called black smokers that were discovered in 1977 by Jack Corliss. A few years later, another kind of vent was discovered called alkaline vents. The black smokers are very hot. They are driven by magmatic heat from underlying fields of lava, basically red hot lava that powers that sort of black steaming that you see there. Alkaline vents, though, are a chemical reaction called serpentinization. But in both cases, these vents have been invaded by life. Many microorganisms and even some larger organisms live on these vents. And of course, it seemed very plausible that maybe life began on vents like this. And that idea goes back over about 40 years now to the early 1980s. There is another kind of a water on the Earth, though, and we call this a hydrothermal field. To the right, you can see what is a place called Bumpus Hill on Mount Lassen, right near where I live here in California. It's about a 3-hour drive north to get to this now extinct volcano, but it does have this beautiful hydrothermal field associated with the original volcanic activity. The important thing is this is fresh water supplied by snow and rain and precipitation. So keep in mind that we think that those two kinds of water, both salty seawater and distilled fresh water, were available on the early Earth as well. So the question is, which would be a more plausible place for the start of life? And I'm going to tell you about an alternative to seawater, which is that life began in fresh water in a field such as you see there. This idea comes back from a place called Kamchatka, which is a sort of a peninsula coming down off of Siberia in far eastern Russia. I've been to Kamchatka twice, visiting a prebiotic analog site. Well, by that I mean we think that this is a place that looks something like what the early Earth was like 4 billion years ago. So here's a trip that I took in 2004 with a group of scientists. We got on a plane in San Francisco and flew up to Anchorage, Alaska. We stayed overnight, and the next morning we took a plane ride to Petropavlovsk, which is a bay on the Kamchatka Peninsula. Kamchatka is a very volcanic area. It's part of the Pacific Ring of Fire, and you can see all the volcanoes. There's about 30 active volcanoes up and down the backbone of Kamchatka. So you can see this little bay again with a yellow lettering, Petropavlovsk, and we are going to travel overland to Mount Matnovsky. And you can see a little line, yellow line pointing to Mount Matnovsky. By the way, when we land in Petropavlovsk, this is a view from the airplane as we came into land. The Koryatsky volcano looms on the horizon, and this little city, about maybe 20,000 people, is just down below that volcano that you see. This is very volcanic area. So there's what Mount Matnovsky looks like from a satellite view. Right in the center, you can see the Mount Matnovsky crater. That's where we're going to visit. We travel overland in a retired Russian troop carrier that is run for people like ourselves to visit these volcanoes. Yes?
Sorry.
Question?
We can't see your presentation. Maybe we can have a little break. After then, we may proceed.
Okay, you want me to stop the talk?
Yes, we can see your presentation. We may have a break and find a solution, maybe.
Oh, I'm so sorry. Let's get back.
Okay, we can see now.
Okay, so if I go like this, can you see it?
Yes, we can see it.
Okay, I wonder what happened. Apparently, when I push play, it doesn't show up as a screen sharing. So this is my first slide that I showed. Did you see this slide?
Yes, we could see that, but we couldn't see after these ones after.
Oh, okay. Well, let me just quickly go over those slides then that you can see now. Is that all? A little technological glitch, but we can find our way. So in this second slide, I show how we fly to Kamchatka, a little town called Petropavlovsk. Kamchatka is a peninsula coming down off of eastern Siberia. Here's a sort of a satellite view showing where this bay is, that we have a community called Petropavlovsk, and we visit Mount Matnovsky. This shows a volcano right next to the city of Petropavlovsk. It just gives you an indication of how volcanic this is. Here we are looking down on Mount Matnovsky, which is the research site that we chose. And here is our little group of scientists that visited Mount Matnovsky. These are grad students and postdocs. I'll point out the guy in the white coat here. That was Vladimir Kompenachenko, and he was our local organizer. He was a volcanologist himself. And this is Megan. She's a grad student at Stanford at the time. This is Jamie Elsila, also a grad student in Stanford. This is Jake and Jan, who were postdocs at the Carnegie Institution. And this is my friend, Tony Hoffman, who did the photographs that you're going to see. So after we camped overnight, next morning we started up toward the crater of Mount Matnovsky. This is a small glacier that we had to get across, and that's Jan and Jake heading up the hill. Here's Vladimir looking down into the crater. So this is my view of what I think the early Earth was like. There'd be volcanic land masses, no continents at that time. There is no life, of course, and there's not much life here, just some bacteria. This volcano explodes every couple of years, so it kind of sterilizes the area. There's fresh water falling as snow, and it melts into the crater. So here now is a little picture of me taking a sample out of one of the fumaroles. I took that home to analyze in our earlier trip, and there wasn't very much there in the way of organic material that might give rise to life. So next time I went, which was this 2004 trip, we found a little boiling puddle, about 10 liters of boiling water on Mount Matnosky. You can see the boiling action here. It's about 10 liters, and around the side is all clay minerals. So we're going to do an experiment here. The experiment is to add organic compounds to see what happens when organic material is available in a little hot spring, such as you see in this slide. So we added 4 amino acids, glycine, alanine, valine, and aspartic acid, 4 nucleobases. These are the bases of RNA, ribonucleic acid, adenine, uracil, guanine, and cytosine. We added an amphiphilic molecule, which is basically kind of a soap molecule, 14 carbon fatty acid, and that's what makes this a milky. That's the soap that is in this solution we're adding, and soap actually is able to form membranes. We think that some of the earliest membranes on the primitive life on Earth were probably using amphiphilic molecules such as this soap that we're adding here. We had some glycerol and phosphate, which we think would have been there. The pH is mildly acidic. It's about the pH of lemon juice, pH 3, and that turns out to be an important consideration. So what we saw within minutes is that membranous froth appeared all around the edge of this pool. See that white stuff that I'm pointing to? Those are a frothy membranes. That soap-like molecule, myristic acid or tetranoic acid, is in fact self-assembling in the membranes. It occurred to me then that maybe life could begin in a wet-dry cycling where this pool would evaporate and then refill and evaporate and refill, and that would just go on many, many times. And perhaps that would kind of pump these organic molecules toward the origin of life. So we published that paper a couple of years later, and if you're interested, you can see the publication. It's in the Philosophical Transaction of the Royal Society. And these are my co-workers. There's a grad student, research associate. There's Vladimir, and we had Stephen Guggenheim from University of Illinois who did work on the clay. So let me just summarize why we think that a freshwater origin is at least as plausible as a seawater origin. First of all, organic compounds accumulate in pools like I showed you there. The acidic pH range is conducive to certain kinds of chemistry, and the concentration of ions is very low, down in the millimolar range, compared to the seawater, which has half molar sodium chloride, for instance, and lots of magnesium and calcium. That is really hard for membranes to form under those conditions. The wet-dry cycles concentrate potential reactants, such as nucleotides that we're going to tell you about in a moment. They tend to polymerize in the dry phase of the cycle, and the elevated temperature provides activation energy to help the reaction go on. Finally, membranous compartments assemble from the amphiphiles, just as I showed you in that little puddle, where those membranes produce a froth around the edge of the pool. Those can encapsulate polymers and produce protocells. Now I want to change the subject and ask, where did those organic compounds required for the original life come from? So this shows the Perseid meteors coming in just last year. This is a sort of a time lapse showing all of these meteor trails coming in over a period of probably about an hour for this to be taken. Now let's take a look at what we think, how that would deliver organic material. We know that 4 billion years ago, these kinds of dust particles were being brought to Earth with a layer of water on the surface. That little blue film is a mixture of ice, methanol, carbon monoxide, and ammonia. In the early solar system, ultraviolet light from the sun would cause a photochemical reaction and produce amino acids, purines, hydrocarbons, and amphiphiles. This would be delivered to the Earth as comets, interplanetary dust particles, and planetesimals during late accretion. The organic compounds would come in with this infall and provide some, at least, of the organic materials required for life to begin. So that is sort of the big picture of how organic compounds could be brought to the early Earth. So this just shows something from Chris Chiba and Carl Sagan. They published this in 1992. You're welcome to look this up. This paper is in, I think this was in Nature in that year, but they did a computational analysis of how much organic material could have been delivered by interplanetary dust particles, by comet impacts and meteorites. So you can see that meteoritic delivery is orders of magnitude less than what would come in on these interplanetary dust particles with this layer of ice and organic material. So we think that probably the IDPs were a major source of organic compounds. So this shows a little overview of just what I've been telling you. We have organic material being synthesized on the dust particles. This dust comes in either as particles or as things like this meteor that you see coming in. It's delivered to volcanic land masses. It accumulates in hydrothermal pools, just as I showed you we saw on Mount Mutnovsky in Kamchatka. And there in that pool, we have wet-dry cycles that allow life to begin. That's the hypothesis. We are testing that hypothesis. Okay, I'm going to skip the next slide because it's a little movie and it won't show. I'm going to go to this slide, which shows something that happened in Murchison, Australia in 1969. A fireball came in over the town of Murchison, Australia. It exploded in the air with a thunderous explosion, and pieces, 100 kilograms of meteoritic little stones and boulder-sized particles hit on the ground. Every one of these red spots you see is where a small boulder fell around the town of Murchison. So we call this the Murchison meteorite, and it has been analyzed by people like myself all around the world. Here's a chunk, for instance, that we had come through our laboratory. This is about the size of a golf ball. It has a fusion crust that you can still see. And when we break it open and analyze it, what we discover is that this meteorite, the Murchison meteorite, contains organic compounds. And that's why we are so confident that organic compounds that are being delivered today as we speak were a major source of organic compounds on the early Earth. Just take a look at what's in it. There are carboxylic acids. Those are very important because this is that soap-like molecule I told you about, where you can actually have a self-assembling membrane. Here are amino acids, about 50 parts per million. There's about 80 amino acids that have been discovered, 10 of which are in life today. There's another kind of compound called amides, along with aliphatic hydrocarbons. These are oily molecules. These are aromatic hydrocarbons, aldehydes, alcohols, and there's even some purines, adenine and guanine, that have been found in a part per million in the Murchison meteorite. So this is really interesting because these are the molecules that are kind of a parts list required for life to begin. So this is what we need to have life begin. We had to have a source of nucleotides that could assemble into nucleic acid somehow. We don't know how this could occur yet, but we do have some good ideas that are being tested. How did nucleic acids first begin on the early Earth? There had to be amino acids present that could assemble into protein-like molecules. And then finally, there had to be amphiphilic compounds that could self-assemble into membranous compartments. So I wanted to show you what a fatty acid looks like. Here is a fatty acid. This one probably has maybe 16 carbons in it if you count them, and this would be called palmitic acid. This is a little too long for the ones we see in the meteorites, which go up to about 13 carbons long, but they are called acids because this head group, a carboxyl group, can release a proton, and therefore that qualifies it as an acid. But now look how much more complex lipids are today. Here's two fatty acids attached to a glycerol, attached to a phosphate, attached to a choline group. Here's cholesterol. These are in membranes today. This is the amphiphilic molecule of life today. So you can see how maybe life evolved from fatty acid membranes into these more complicated molecules, such as we see here. We don't know how that occurred yet, but of course, people are thinking about it. Let me show you some membranes that everyone who's listening to this has seen in their life. Soap bubbles are membranes. When you blow a soap bubble as a child, those membranes self-assemble from amphiphilic molecules. And when I show you membranes that we work with, you're going to see basically a kind of a soap molecule which is able to assemble into microscopic membranes. We call these lipid vesicles. Now, the next slide is another movie, so I have to skip that. And I'm just going to show you how a soap molecule would look like if we could see the molecules in the membrane. So you can see water molecules, just to give you an indication of the size of these things. That's H2O. So you can just imagine this is all water on this side of the membrane, all water on this other side of the membrane, but the membrane itself is composed of hydrocarbon chains. And this is the real barrier that membranes provide for life. These are very important barriers so that the membranes are not freely permeable. This makes a permeability barrier that's very important to all life today. These darker gray are the head groups of the lipids on either side of the membrane. So here's something that I'm so interested in just what we see here. The reason is that years ago, we extracted organic molecules from the Murchison carbonation meteorite, and these are membranous vesicles that can form from that Murchison lipid-like molecules. So we know for a fact that even though these things are probably over 5 billion years old, they still retain the ability to assemble into these beautiful little membranous compartments. And over on this side, you can see we've encapsulated a fluorescent dye, and these really are membranes. They don't just leak everything that is inside. They can encapsulate and provide a permeability barrier to things that are inside. These compartments are required for the origin of cellular life. If we did not have these available on the early Earth, life could not begin. Now, here's an important thing that you have to understand to know what we're going to talk about next. If you dry membranous vesicles in the presence of a solute, such as a nucleic acid or a protein or simple molecules like amino acids or nucleotides, when you dry it down, these membranes fuse into a multilamellar structure, and the things that were outside the membranes to begin with are now captured between these multilamellar structures. When you put water back in, the vesicles reform, but now the stuff that was outside has been captured inside. So I want to show you how easy it is to do this sort of a thing. And this is why we think that this kind of encapsulation was very important to the origin of life. Here we have taken a fatty acid, decanoic acid. It's a 10 carbon acid. Decane, of course, means 10, decanoic acid. And we mix it with some DNA in about a 1-to-1 ratio. We put it through a single dry to wet cycle, and the DNA has now been captured inside the vesicle. We stain the DNA with a fluorescent dye so you can see it. So that's how easy it is if you have polymers, a single wet-dry cycle with an amphiphilic molecule like this very simple fatty acid can give you what we call protocells. This is a step toward the origin of cellular life, and we think that this is a well worth following up in our research, which is what we're doing now. So let's talk now about where nucleic acids could have come from on the early Earth before life started. I really think that nucleic acids are not an invention of life. I think that nucleic acid probably were available before life began, and that nucleic acids actually were part of the process of assembly of protocells. So if we could make these on the laboratory or in prebiotic analog sites, which we're doing now, it might help us understand how life could begin. So here's the question. This is why this is such a tough problem. Where did nucleotides come from? These are the monomers of nucleic acids, but they're pretty complicated molecules. So we don't know really where nucleotides could come from, but we're trying to figure it out. There are scientists now addressing that question. Then the next question is, what source of free energy could drive condensation reactions? And this is the ester bonds that form between nucleotides to turn them into nucleic acids. So that's an open question. Nobody knows. I'm going to show you how it might happen, but it's not something that we understand yet, how the nucleic acids could have self-assembled on the early Earth before life began. Then we have the question of entropy. Everybody knows that entropy tends to increase over time. Things become more and more disorder. We call that an entropy barrier because life is orderly. How do we go from the disorder of a sterile early Earth with lots of mixtures of organic compounds? How do we overcome that disorder to make the order required for life to begin? Finally, how can life resist hydrolytic degradation? If we make nucleic acids, why don't they just break down right away? That's a real problem. We call that the water problem because water hydrolyzes nucleic acids. So we do have an answer to that question, and I'll tell you about that. Then this is the big question. How did nucleic acids evolve function, such as catalyzed growth and replication? If we can answer that question, we will know how life can begin on a habitable planet like the early Earth. So that is still a completely open question. We don't yet know how that could happen. There's a few ideas, but nobody knows with any certainty. But these first four, I think I can provide an answer to. So let's now take a look at how we're going about this. So I showed you that freshwater hot spring that gave us this idea on Kamchatka. We're going to put up a hypothesis and test it in the laboratory. We're going to expose mononucleotides to conditions simulating the wet-dry cycles we see in hydrothermal fields. And those conditions are a carbon dioxide atmosphere. We don't want to have any oxygen around because the early Earth was anaerobic. We have to heat it up, elevated temperature, not quite to boiling water, but up close to boiling water. That's 85 degrees Celsius. It's got to have a acidic pH range. This is conducive to condensation reactions, and we have to have multiple cycles in which you wet things and dry things, wet things and dry things. Here's the apparatus we built to make this happen. This is a simulation chamber in which we simulate the wet-dry cycles that we see in hydrothermal fields. This is a rotating disk. It rotates very slowly, maybe about 1 revolution per hour. There's a little motor underneath that drives the revolution, and it goes maybe from here to here is about 7 degrees. It takes 15 minutes to go that far. There's a heat source, just a laboratory hot plate. There's gas coming in from a gas cylinder. It goes into these little tubes that go down into reaction mixtures in little vials that are held in these wells. And then there's also a hydration cycle where a perfusion pump is dripping water. So every time one of these things goes past that little tube, there is water dripping into the reaction mixture. So it takes about an hour to go from here all the way through to here. To first you dry it out under CO2, then you make it wet again. So here's something you've got to know. This is the chemical reaction we're trying to make happen, because this is the chemical reaction that makes nucleic acids from nucleotides. Any organic chemist knows this reaction. This is really easy to do. If you mix some ethanol with acetic acid, it will turn into ethyl acetate. Ester bonds will form spontaneously, and water will come off as a reaction product. The same thing should happen with a nucleotide. This is adenosine monophosphate. Here's an acidic group, phosphate group. Here's an alcohol, an OH group on the ribose of this AMP. If this can get close to that, if we can concentrate this, a water molecule can come off and we will form an ester bond. So it's as simple as that. We're trying to pull this reaction to the right. And if we do it long enough, and if we have enough cycles, and we have water evaporating, allowing this reaction to be pulled to the right, we can make nucleic acids. So that is the hypothesis we're testing, and I'm going to show you just a few results that we have so far. Here's the way we test it. We have mononucleotides. We can have lipid present if we want. We have a low pH, pH 3. We do multiple wet-dry cycles at elevated temperatures. We isolate the products. These are polymers. We can label them with radioactive phosphate and some enzymes, and we do what is called gel electrophoresis, where we separate whatever the products are on a gel. Now, if we had done this with real RNA, we would end up with RNA with radioactive phosphate on the end. So the question is, are the molecules that we make by wet-dry cycling, are they the same as real ribonucleic acid? And here's the answer. They are. We can end label the RNA that we make using these enzymes. We can make them radioactive. And here is a experiment we published back in 2008. And my co-author in this was Sudha Rajamani. She did this work in which our products were labeled with radioactivity. So here's 1 cycle, 3 cycles, 5, 6, 7, and you can see more and more of this radioactive product being produced. And look how long it is. We start seeing them at around 10 nucleotides on this ladder that tells us how long they are. They go all the way up through about 50 nucleotides on average, and they go as high as 100 nucleotides. Everything else you see here, each of these is one experiment where we vary the temperature in this case. where we vary the kind of lipid. This is phosphatidylcholine, phosphatidic acid, lysophosphatidylcholine. Then down here, we vary the ratios. So every time we did this, it worked. So this is a very, very repeatable experiment. Other people are now repeating this work. We can also see them by fluorescent labeling. Here's our product picking up a fluorescent label, just as RNA does in this gel. Here is a known polymer of RNA picking up the fluorescent label. We did this in 2 different experiments. This is with ethidium, and this is with another kind of a dye. And here's our product again. So this is behaving just like RNA should behave. Okay, my last set of slides now has to do with a new way to analyze this. And to me, this has been convincing that we are really making nucleic acids without using an enzyme. Years ago, we invented a technique called nanopore sequencing. And you can now buy nanopore sequencers. The smallest one is called a MinION. They're manufactured by a company that licensed the patents from us, and they are making these and doing very well, marketing these globally now. So here, the way it works is that we have a nanoscopic pore. Here it is. It's one that was developed by the company. Here is a helicase enzyme, and a helicase uses ATP to unwind a double-stranded molecule and allow it to go through the nanopore at about 50 bases per second. The nanopore has an electrical current flowing through it in the form of ions that are present in the medium. Here is a single base resolution that shows the ionic current changing as each base advances through it. So this might be thymine, for instance. This might be guanine. This might be cytosine and adenine and so forth. So from this, we can get the sequence of a single strand of nucleic acid in about 450 nucleotides per second. This is really a wonderful thing for us to work with. So we're going to use this in this last experiment I want to show you. This experiment, we actually asked whether we could make DNA from a single monomer of DNA called thymidine monophosphate. We put it through multiple wet-dry cycles. We think that we made oligothymidyllic acid, where these were all lined up in a strand. These are too short to do with the nanopore sequencing by themselves. So we attached these by ligation to a known strand of DNA, and then we put it into our nanopore sequencer. So this is what the sequencer looks like. It's called the MinION. It costs about $1,000. Here's some DNA being put into the nanopore sequencer, and then the sequencer is attached to a laptop computer, and you can actually watch single molecules of DNA being sequenced on the computer screen. And this is what a single molecule looks like as it passes through the pore. All of these ups and downs are the bases causing a change in the ionic current as the enzyme passes them through the pore. So you see it go up and down, up and down. This is that DNA that's attached to our T, to the oligo T that we're looking for. And then suddenly everything stops going up and down, and we just have this going through. That is the oligo DT that we have made by this wet-dry cycling. Finally, then the strand leaves the pore, and you can see this here. We then ask the computer to do sequencing of what it saw going through. So here is radioactive labeling of our product, and here's a scan of that gel, and you can see that we go all the way from 30 mers down here, all the way up to over 90 bases long. Each of these radioactive lines then is shown up in this scan of that particular gel. These short ones, this is about 30 mer here. If you counted up all of those guys, it's down in this range. This is down in the 40 mer range if you count them up, and here is in the about the 80 mer range if you count all those up. So we're quite certain that we actually have made oligo tea just by wet-dry cycling. Finally, if we put a lipid in, we can see the DNA accumulating in the lipid vesicles. So here is lipid membranes. We got AMP and TMP, so this is making this mixture of DNA. After one cycle, we see some fluorescence accumulating. Here's 2 cycles, 3 cycles, and finally 4 cycles. The fluorescent stain is DAPI. This is specialized for DNA. And now you can really see the DNA accumulating in these vesicles. So I think this is what the most primitive form of life looked like. It had something like a nucleic acid encapsulated in a membrane. It's microscopic. These are about 10 microns across. And somehow the DNA or whatever nucleic acid was there learns how to reproduce itself, probably by interacting with peptides being produced and forming an enzyme that can catalyze the synthesis of DNA. If we can get up to that in our research, if we can find ways for that material that you see there to replicate itself, then I think we will have an answer. We will know how life can begin on a habitable planet as long as it has those compounds available, and wet-dry cycling. So that's the end of my talk. I'm going to turn off my screensaver. Let's see where I turn this off. I'm used to using Zoom, so let me just see you. And can you see me now? Hello?
Yes, we can see you.
Okay, good. Well,
Sir, thank you very much for this delightful presentation. Now it is time for the questions. The first question is, doesn't very high temperature pose a threat for life?
Does it cause what for life?
Doesn't very high temperature pose a threat for life?
Oh, okay, a threat. Good. Good question. Well, there's a kind of an easy answer, because when we go to these hot springs, there is life in it, all the way up to about 90 degrees C. And down in those hydrothermal vents, the world record for life high temperature is 121 degrees above the boiling point of water down there in these hydrothermal vents. So life is not inhibited by high temperatures. Life can adapt to high temperatures. And the colors that we see in these hot springs are produced by films of microorganisms that easily survive 80 to 90 degree temperatures.
Thank you. The next question is, what is the importance of pH on the experiment?
Very good question. It has a chemical answer, so I'm going to have to use a little chemistry and hope that I can explain it to you. To make an ester bond, I showed you a slide that water has to leave in order for the ester bond to form. That's called a condensation reaction. At high pH, the phosphate on the ribonucleotide has a negative charge. It's, instead of being an OH coming off the phosphate, it is O minus. That cannot form water. So I have to bring the pH down to what's called the pK of the phosphate group, which is down around pH 3, and there the phosphate OH group is there as an OH. And now it can pick up a proton and become H2O and come off. So the acidic pH, and by the way, it's not really strongly acidic. This is not hydrochloric acid. This is a weak acid, and the pK around pH 3 is the place where the phosphate can release the water as a leaving group and allow the ester bond to form.
Thank you, sir. The next question is, we are emphasizing that life without water is not possible. If an opposite example is found on other planets, what would this change in the world of science?
Well, one thing to keep in mind is that although life requires water to go through a cycle of life to reproduce, life can survive being without water. If you buy some seeds for some tomato plants down at the nursery, those seeds are dry, but they are dormant life. As soon as water comes back after you plant them, they sprout and grow up into a tomato plant. Some animals can do this too. Animals called tardigrades can completely dry up and exist completely dry for years, in fact. When water returns, they pop back out and away they go. So although water is necessary for life to go through a life cycle, it's not necessary for life to survive. And of course, bacteria make spores, which we know for a fact can survive outer space conditions. There's a thought that maybe, this is just a fun thought, maybe life began on Mars and was delivered to the Earth as bacterial spores on a Martian meteorite. That's quite possible. It could be that all life on Earth actually goes back to Mars. And so keep that in mind. I think that's a wonderful idea, and it might even be correct. We will know as soon as we discover life on Mars, if it ever existed there.
Thank you. Our last question is about protocells. They are said to be the first cells-like structures that might have occurred in the evolution from chemistry to biology. Could it be the case that RNA, which carries ribosome function, was encapsulated to create the first living cell? Would that be thermodynamically possible?
That's a very knowledgeable question. Whoever asked it knew about ribozymes, and they were thinking very well, saying that maybe ribozymes were part of the first form of life on the Earth. And that brings us to what is called the RNA world. Years ago, when ribozymes were first discovered, people immediately said, well, maybe ribozymes came before DNA, and maybe ribozymes were the first catalyst that allowed life to begin. And in fact, a scientist named Phil Holliger, who works at, I think he's at University College London, has discovered that ribozymes, there is a catalyst that can act as a polymerase. So ribozymes can be a catalyst to make more RNA. So we're getting along, step by step, experiment by experiment. We are getting closer to the possibility that we will have ribozymes in a protocell able to reproduce themselves by a catalyzed reaction. But there's really much more to it than just what I said, because there had to be a way to activate the monomers. All life today requires chemically activated monomers to make new proteins or new nucleic acids. Chemical activation requires metabolism. And what I just told you, I didn't say anything about metabolism. Holliger's experiments are just adding activated molecules all ready to go. But we don't know how metabolism could begin yet on the early Earth. That's an open question. And I hope maybe some of the people listening would say, I want to work on that for a scientific career, because, boy, that would be a wonderful career to get into.
Thank you very much. That was all for the question part. Sorry, it was a pleasure to have you here today.
Thank you very much for the invitation.
Thank you. Dear participants, this was the last presentation of second Astrobiology live presentation series. Thank you very much for being with us with this series. We hope to see you face to face next year. Until then, stay with science.